Fermat's last theorem plays a very interesting role in pedagogy. Today, every student can make a discovery by looking at a school globe or at a wooden cube. Are there any short and simple ways to prove last theorem? Do we need to spend 100 or more pages and help of artificial intelligence to find a proof? Beyond any doubt, neural networks are a very useful tools for broadcasting knowledge among billions of people. Thus, Bob and Alice will help us.
The Fermat's last theorem plays a very interesting role in pedagogy. Nowadays, every student can make a discovery by looking at a school globe or wooden cube for child. In this video, let's consider the following questions. What is topology and set theory? Why a ball and a cube are homeomorphic? And what homeomorphism is? We'll discuss the irreducible conflict between form and content which is embedded in this theorem. Then we will make generalizations and conclusions about the fundamental properties of our universe. Begin from the beginning. Fermat's last theorem was formulated in 1637, and it states that this equation for the whole numbers a in degree n plus b in degree n equals c in degree n has no solution for n greater than 2, except 0 values. This theorem was formulated by Pierre de Fermat in the margins of the book Arithmetic by Diophantus of Alexandria in the 3rd century A.D. Thanks to Diophantus, we treat algebraic equations as it is convenient and familiar to us. French mathematician, Pierre de Fermat, wrote in the margin of the book, "I have discovered a truly marvelous proof of this, which this margin is too narrow to contain."
Then, in the 1990s, Princeton mathematician Andrew Wiles shocked the world with a breakthrough. Standing on the shores of number theory, he began dreaming of a bridge to harmonic analysis. They also showed that Frey's elliptic curve can't exist, which means that a solution to Fermat's equation can't exist either.
Subsequently, descendants denigrated the French mathematician and believed that he made a lightweight judgment, simply put, bragging and lying.
I'm Andrew Granville. I work in analytic number theory. When I was young, I worked on Fermat's last theorem before it was proved. Today, I work in ideas of L function.
You cannot prove them because you cannot go back to anything more primitive than those propositions themselves. They are not in need of justification.
There's this particularly famous example by Peter Schulze. He had a very, very difficult proof that he wasn't 100% sure of. He would try and say, well, this is true, and you should know this, Lean, and Lean would say, I don't know this at all, you're going to have to explain this better. The bits where
the basis for such an assertion was a 100-plus page proof by Andrew Wiles, prepared by him in 1994. The question arises, are there short and simple ways to prove the Fermat's last theorem? To understand this, is it necessary to waste 100 or more pages and help of artificial intelligence? We refer to 500-page work of Shinichi Mochizuki, Japanese mathematician working in number theory and arithmetic geometry from Kyoto University, dealing with the ABC hypothesis in number theory. But there is another approach. Min-Hyung Kim, a mathematician at the University of Oxford, said it should be possible to use ideas from physicists to solve problems in number theory, but we haven't thought carefully enough about how to set up such a framework. And one more, his quotation, we're at a point where our understanding of physics is mature enough, and there are enough number theorists interested in it, to make a push. To the posed question about short and simple ways to prove the Fermat's last theorem, the answer is yes. And this method is associated with a mental experiment. Consider a construction of 3 concentric nested n cubes or balls, with centers at the origin, with edges or radii just equal to natural numbers a, b, c. Why these whole numbers, which are mentioned in the last theorem, will necessarily be different. Suppose the opposite, if the first 2 terms are equal to each other, then in this case it is easy to see that the root of 2 must be represented as a fraction, say p and q. Let's reduce p and q by greatest common divisor and they become mutually prime numbers. But then we go to this equation and make sure that we have an even number on the right and left sides. For instance, if degree n equal to 2, The right part is divisible by 4 because here p squared is the result at least twice prime number 2. So divide by 4 the right part of equation and make sure that the left part must also be divisible by 2 and again by 2. Thus p and q become even and we have arrived at a contradiction for the case of degrees higher than 2. The proof is quite similar, so it is no less general to put that whole numbers a is less than b, which in turn is less than c. 3 years ago in 2020, I formulated a proof of Fermat's last theorem, which is that if you take the 3 n cubes here symbolically depicted on the plane a small cube, you layer around it a certain number of unit cubes. Create the b middle cube, layer another certain number of layers, create c large cube, where volume of a small cube is equals to volume of difference of c large and b middle cubes. It is easy to make sure that in the project of a house for a capricious rock star, the condition of equivalence of the volumes of the studio and the winter garden excludes central symmetry, and vice versa. And you get a construction that doesn't really exist in nature for the case n greater than 2, it's amazing. You will never be able to put each unit cube from a small n cube in correspondence with another unit cube of this subset of layers between the middle and the large one in such a way that you do not destroy the symmetry of the construction and do not allow voids. Generally speaking, these subsets are not equivalent to each other. This is the main idea of the proof. This is due to the fact that this figure has the property of central symmetry and does not contain inhomogeneities. As a result, each layer in this figure is not comparable to another layer. Thus, each layer in this figure is not reducible to another layer. Here additivity conditions and axiom of measure do not work. In other words, it is impossible to speak about addition of volumes. Why did Andrew Wiles need over 100 more pages to prove it if half of page is enough, or 6 faces of wooden cube for child? Ross Patent put me guilty of plagiarism with Andrew Wiles' proof, for which he received an Abel Award in 2016. Ross Patent refused the state registration of a patent for an industrial design under the pretext of violating public morality. Ross Patent's claim about plagiarism of the proof does not stand up to any criticism because the proof you see is original, new, and it really breaks the stereotypes formed in science about the absence of a short proof of Fermat's last theorem. Let us imagine that we have concentric spheres nested within each other, spheres with the natural radii a, b, c that we are looking for. We will distinguish between a ball and a sphere that encompasses the ball. The sphere is the so-called layer for the ball, so the above notations are adopted here. Here is the ball and here is the sphere. A layer, it has dimension 1 unit less. This is clear from physics and math courses. Remember the formulas for the length of a circle and the area of a circle, the area of a sphere and the volume of a ball. It is interesting to imagine that in the one-dimensional world we would have such an open ball in the form of a segment, excluding its endpoints or zero-dimensional spheres located at a distance r from the origin. Now for the case of the two-dimensional plane, the open ball becomes the familiar circle, excluding the one-dimensional sphere already considered. Finally, for the three-dimensional case we have the usual ball resembling a soccer ball. It is closed by a two-dimensional sphere. We again exclude an arbitrary meridian from the sphere. As a result, we got acquainted with the sequence of geometrical elements on the sphere of dimension from 1 up to n-1. These are the so-called hypermeridians, which will be useful for us in the future. Let's continue the experiment with the cascade of spheres. This is the encompassing meridian. Let's try to change the step, for example. What happened? And this is the code that allows us to create this design. It's based on an understanding of set theory. Now let's look at the basics of set theory and make a small generalization. If a triple of natural numbers a, b, c exists, c existence quanta for a brief notation, then in this case we can map every point of space from this interval between the middle ball and the big ball into a small ball. And since this whole construction is symmetric, this means that every sphere that surrounds these spheres can be mapped into many other spheres. The Fermat's last theorem states that this is impossible. Why? Because that's the physics of our universe. It manifests itself in the topological properties of figures. Let's talk about continuous functions and relations that work in topology. Topology is the science of geometric objects that modify these objects in the most arbitrary way, but nothing breaks, and all transformations are reversible. Here you see the Russian figure skater Kamila Valieva. She is plastic. She performs a beautiful smooth dance. Let's imagine a certain function f mapping the set x to the set y. Similarly, you can see how Kamila performs different figures and these mappings are reversible. You can scroll the movie backwards. Each image has a pre-image. In this figure, a point can have an open neighborhood. This neighborhood of point A is mapped entirely to this neighborhood of point B. This is the definition of continuity. Speaking of homeomorphism, we note the interesting transformation of a mug into a torus and vice versa. A little more information from set theory. One more the simplest numerical examples. This is the notation of a set and its members. These are the operations of intersection, union and subtraction of sets. And this is the notation of an empty set. Here is the notation of a universal set. In the Euler-Wien diagram, the universal set corresponds to the whole rectangle. This is the set A. And this set is the complement of A, but Y only numbers. Let's move on to the three-dimensional expression. 3D modeling offers great possibilities. We can see the operation of combining two cylinders. By replacing only one operation, we got another construction, when another cylinder is carefully cut out from behind one cylinder. Now the next variant of intersection of sets a cylinder cut out of another cylinder.
When working with three-dimensional figures, you can see the advantages of knowing the basics of set theory and, in addition, check the effect of distributive rules, when expressions can be rewritten in two ways. For example, it is easy to get a cascade of spheres. And here's the expression we're looking for. It's a famous triple number called the Pythagorean triple, 3 squared plus 4 squared equals 5 squared. This one is just the sides of a right triangle. There are infinitely many such numbers, they form an uncountable continuum. Pythagorean triples were known to mankind thousands of years before the birth of Pythagoras himself, from the time of the Sumerians, who used them to easily solve trigonometric problems. The Fermat's last theorem states that Pythagoras triples exist only in the plane.
Proving the opposite, let's try to visualize in volume. This is a small ball with radius 3. This is a medium ball with radius 4 centimeters, and this is a large ball with radius 5 centimeters. Let's subtract from a large ball point collection of medium ball. Look, and here's a big enough cube to cut our construction. Let me remove it and here's the result. Imagine that here we've cut the figure, we can see it in a slice. The power of a set plays a key role in finding a proof of Fermat's last theorem. The concept of power of a set is easy to understand with examples. Imagine that we have set A of triangles and the set C of cylinders. These sets are called equal power sets because they have the same number of elements, which is denoted by these symbols. A is equivalent to C. The following is an example of different power sets. It is easy to understand that the set of natural numbers is equivalent to the set of whole numbers because each pair plus and minus 1, plus and minus 2, plus and minus 3 and so on is numbered with one number. Such a set is called a countable set. The set of natural numbers is countable, and the set of rational numbers is also countable.
The mathematician Georg Cantor proposed an original way to circumvent each number as a fractional division P of Q. Imagine a big movie theater in which there are rows P and columns Q. You go around this movie theater like a checker to find a stowaway. But you follow the diagonals obliquely going, for example, to the upper left corner, and now you start moving along the zigzag line and gradually examine each seat in this infinite movie theater, you will find a stowaway. Thus, the set of rational numbers Q is countable. For the case of real numbers, which also include irrational numbers that cannot be represented as fractions, this is not true.
It is important to remember that when we talk about relations of continuous and mutually reversible functions, it is allowed to compare only spaces of the same dimensions. For example, let's take a pencil. You can imagine a point source of light that illuminates it from above, and this pencil is mapped into a point, but you can't do the inverse transformation from a point back into a pencil, because the principle of mutual unambiguity is violated here. The antipode of mutual unambiguity is, for example, the operation of measure over sets or the volume of a figure. Summarizing the above, we can conclude a point cannot be equivalent to a segment to a square or a circle in the plane, and these last figures to a three-dimensional cube. It is possible to put a continuous mutually unambiguous correspondence only between figures of the same dimensions. The same principle applies in a discrete space consisting of elementary cubes. In the digital age, we can supplement Euclid's postulates with the following elements derived from elementary unit cubes lined up in a row: a rectangle, a three-dimensional cube, and so on. Don't forget that we are working in n-dimensional space. The dimensions will be as if we were dealing with points. This is a clear demonstration of the correspondence principle in science. A little more from the theory of topology. Imagine that we want to work with a constructor, something like a Lego constructor. The union of any family of sets belonging to the set omega also belongs to the set omega. The intersection of any finite family of sets belonging to the set omega also belongs to the set omega. The empty set and all X also belongs to omega. This is the definition of topology. The elements of the set omega are called open sets of the topological space X and omega. For simplicity, we can abbreviate it by simply writing X, omitting omega. We will find it convenient to work with such a constructor. Let us return to the search for the proof of the last theorem. Let's imagine nested balls. They are defined by the equation x squared plus y squared less than radius r squared. We mean open balls, because the spheres themselves that enclose the ball do not belong to this set. For the n-dimensional case, everything works the same way, but here instead of 2 coordinates there are n coordinates. The sum of their squares is still less than the radius r squared. What about cubes? The picture is not fundamentally changed, just used a slightly different metric, where instead of the square is substituted function maximum value of x or y less than the radius r. For the case of n-dimensional space, we will have n variables listed here. This is a sphere of dimensions n-1. This is also a sphere, but of smaller dimension. It is not by chance that there is a sign of homeomorphism of figures here. The structures defined by these bases coincide. They say that metric topology is defined here, and we have obtained a metric space. So a ball and a cube are the same, only slightly deformed in topology. Compare these cubic watermelon and rounded cube.
Another important concept is openness and closeness. Suppose we have a set F in X. It is closed in X in omega if its complement, denoted as F minus X, is open and the complement itself is also subject to omega. Now let's go back to our notation. Here is a n-dimensional ball. Point A defines the center of this ball. The radius of the ball is equal to r. Here ρ denotes the distance from point X to point A. This ball contains points no more distant than radius r. A closed ball is denoted by the letter d. Everything is similar to the above, but only here the sign is less than or equal to r. Finally, a sphere is a set of points located exactly at distance r. Note that the dimension of a sphere is 1 unit less than a ball, which continues the tradition of the 3-dimensional case and the 2-dimensional case, which is well known to us. Here you see a very beautiful fractal set of Mandelbrot, which is defined by a recurrence formula and differs such fractal sets from our usual sets in that as you increase the scale of the set, the same features are revealed infinitely repeated. Imagine you're looking at a map from a bird's eye view, then you go down, you get closer to this object, you see more and more details, so these details show an even more complex structure. It repeats itself all the time. There are no arcs, no smooth curves or straight lines. So the dimensionality of this fractal set is fractional. It's amazingly beautiful. I gave this example to illustrate that the boundary of a set is not as trivial as it seems.
Let's look at a few options. Suppose we have a set A. This point number 1 is internal because it belongs to this collection of points along with some neighborhood. Point 3 is external because we can find a neighborhood that does not belong to this set. And this point 2 is on the boundary, because it contains a neighborhood of points that both belong and do not belong to this set. The neighborhood can be arbitrary, not necessarily in the form of a sphere, the main thing that it was an open set. From the theoretical digression, we return to the proof of Fermat's last theorem. To do this, we need another model. Let us imagine that we dissect our n-dimensional sphere by hyperplanes. Let us start with the simple case of four-dimensional space. What do we see here? This three-dimensional sphere centered at the origin is the result of intersection of four-dimensional sphere with three-dimensional subspace or hyperplane. You can see the orange equator on the sphere. Here we see the northern and southern hemispheres. The equator is excluded. The equator becomes a meridian when you turn it 90 degrees. Now let's focus our attention only on the two-dimensional hyperplane or, simply speaking, on the ordinary plane. In this subspace we have two arcs of a half circle. Focusing on the one-dimensional subspace or line, we finally get 2 points corresponding to the one-dimensional sphere. So, we have a space, which includes a hyperplane of dimension 1 unit less than the degree n-1. In turn, this subspace includes a subspace of dimension n-2, and finally, in this chain, we descend to a two-dimensional plane, a one-dimensional line. In elementary school we study the cut of a cut tree, the layered structure of the Earth's crust in a section, the traces of layers on a probe taken out of a super-deep well. All these are examples of induced topology. In our construction of a set of continuously following spheres forming open spheres, regardless of size, always a large sphere contains a smaller sphere, in its turn a smaller sphere, and so on. A similar pattern of nested layers like the Russian Matryoshka doll can be seen on the two-dimensional plane piercing the n-cube. It is not by chance that I say piercing and not dissection, because, from the basics of linear algebra, it is easy to understand that a cube is dissected by such a plane into two disconnected space. Starting from the tesseract, a two-dimensional plane can be encompassed by a continuous contour transversely located to it. The picture resembles a baked apple on a skewer. Unfortunately, this revealing fact is not understood by some scientists when they encounter a chain of n-cubes nested inside each other.
For the ball situation is self-evident. But we have seen that in topology a ball and a cube are homeomorphic to each other and are easily transformed into each other as a result of deformation without breaking the space. When we subtract a meridian from a sphere and get two hemispheres, when we consider upper and lower half circles with open ends, the dimensionality of the figures does not change. For the three-dimensional case, we can place the point source at the origin and conclude the figure understudy to the upper and lower tangent planes. A beam of light pierces each point of the southern or northern hemisphere and displays a shadow on the lower or upper planes. The meridian or equator would correspond to an infinitely distant point. For the two-dimensional case, the picture is similar. A ray of light corresponds to each point on the tangent line of an arc with open boundaries. It is easy to see that the dimensionality of the sphere S or layer, minus the meridian, will remain 1 unit less than the ball covered by the sphere. Indeed, from the school course the length of a circle is 2 pi r and the area of a circle pi r squared, the area of a sphere and the volume of a sphere, and in the general case the dimension of the layer we are studying is m-1.
It turns out that on a perfectly smooth homogeneous surface of an n-dimensional ball there are geometric elements of all dimensions from 1 to n-1. These are hypermeridians. What happens when they are continuously mapped into a set of other spheres, following sequentially from the radius of the mean to large or in another interval of radii, as in the drawing obtained earlier by the D-modeling? The simplest case is illustrated by the good old reel-to-reel tape recorder, where the tape is rewound from the left reel or spool to the right reel or vice versa. In this case, the sum of the areas of the tape circles on the left and right remains constant and is equal to the thickness of the tape multiplied by its length. Let's assume that we have caught the moment when the tape reel has a larger radius on the left rather than on the right. If we speak about the necessity of preserving the symmetry of the figure at continuous display or moving of a layer, It means that one turn of the tape on the left should fit into the whole number of turns on the coil on the right 2, 3, 4 and so on, but not fractional. Otherwise the condition of preserving symmetry at moving, displaying of layers will be violated. Indeed, the layer filled partially has a symmetry defect. It is asymmetric. If we can produce a tape of arbitrary thickness, then for any predetermined ratio of radii of coil circles we can easily achieve symmetry preservation in this model. Namely, one layer or coil on a large coil is equivalent to a set of complete coils or layers on a small coil. For the case of a n cube of dimension 2 or, more simply, a square in the plane, the picture is similar. By virtue of symmetry it is convenient to focus on the study of only one segment formed by rays emitting the beginning at two adjacent vertices and apply the formula for the area of a trapezoid through the product of the length of the midline by its height. As a result, both the volume, the power of subsets, in the form of a layer mapped into a set of successively and continuously following layers, and the symmetric form of the structure are preserved. What prevents us from making a similar experiment for the case of 3 and more dimensional space? To answer this question, it is necessary to familiarize ourselves with the concept of pairwise disjoint equivalence classes.
Here you see a picture of the Taj Mahal, a monument of Indian architecture. It has symmetry with respect to the vertical axis passing through its center. We can say that the mirror just plays the role of an equivalence relation. Symmetry is one of the types of equivalence functions. There are other examples, such as homeomorphic figures already familiar to us, such as displacements, rotations, and so on. Note that the Taj Mahal is made up of different elements, columns are mapped into columns, domes into domes, and there is no mixing. Or take chess. While the game is played on parity, pawns are exchanged for pawns, light pieces bishop, knight, for light pieces, heavy pieces rook are exchanged for rook or queen for queen. These are pairwise disjoint equivalence classes. The equivalence function deals with each class separately. It is easy to prove strictly mathematically. There is no mixing going on.
Applied to our construction of 3 concentric balls or n cubes. Arbitrary element of each dimension can only be mapped by the equivalence function into an element of the same dimension. Let's focus on the formula layer is mapped into many layers. Each element in preimage must map into image as set of elements of the same dimension. It is more usual for high school students to talk about integration, but the application of higher math will be unnecessary here. When explaining the integral, teachers often operate with the notions of splitting a figure into separate pieces or differentials, like cutting a lemon, which are later reassembled into a whole. In other words, there is a similar construction to what we have done. A set of successive spheres around the origin point form a ball. Similarly, a set of layers of a n cube form the n cube itself. The structure of the layers is determined only by the dimensionality of space and does not depend on the geometric size of the layer. For simplicity, let us consider a sphere encompassing a 3-dimensional ball or a layer encompassing an ordinary 3D cube. Here there are elements of dimension 2 hemispheres, faces, and elements of dimension 1 meridians and edges. The condition of equivalence or equality of volumes of the mapped layers means that each arbitrary layer from a large sphere can be mapped into a natural number of layers of a set of continuously following small spheres. Recall our experiment with tape reels. The number of layers in the image is greater than or equal to 2, since 2 is the natural numbers following the unit. This leads to a system of equations that is unsolvable even in real numbers. You can verify this by using the triangle inequality, where the sum of the lengths of the cathetes is greater than the length of the hypotenuse, except for the zero case, which is excluded by the conditions of Fermat's last theorem. For the number of terms more than 2, apply the assimilative law and mathematical induction method. What fundamentally changes for the n-dimensional case of n greater than or equal to 3? The number of equations in the above system becomes n-1, but it also remains unsolvable. In other words, when the number of equivalence classes is greater than 1, 1 is the 2-dimensional case of the plane. It is impossible to ensure simultaneous fulfillment of the conservation conditions for the shape and volume of the layers being compared. In the n-dimensional case, the concept of measure is introduced instead of volume. The layers can be ordered. It is an ordered chain of sets, but it is senseless to speak about arithmetic operations of addition, subtraction, reduction here.
Skeptics may object concerning somewhat artificial separation of hypermeridians from the sphere. Why do we need such complications, if the sphere, a smooth figure, defined only by the radius? Note in passing that, for the case of a hypercube, the statement about disjoint faces or equivalence classes of A is multiplied by unit to the power n-m seems to be more natural and obvious. But in the latter case, the very dimension of the face is under attack, appearing to be simply equal to the dimension of the original space. In fact, if Fermat's theorem is true for triples of whole numbers, then the units do not matter, be it meters, centimeters, millimeters, micrometers, nanometers, etc. This means not only equality, but also the identity of the equation of Fermat's last theorem, or in other words, the independence of the output from space partitioning. A unit cube can be made as small as you like, but the essence of the phenomenon will not change. I will repeat again, in the digital age it is possible to supplement Euclid's postulates with elements derived from elementary unit cubes lined up in a row, a rectangle, a three-dimensional cube, and so on. Note that we work in n-dimensional space.
The dimensions will be as if we were dealing with points. This follows from the principle of correspondence in science and the basics of differentiation and integration, which we will not touch upon. Separation from a figure, let's say from the sphere S2 of its element, a subset of S1, for example, the equatorial circle. That is a legal technique familiar with the elements of Euclid from the 3rd century BC and school geometric courses on the plane, stereometry and drawing. Let us continue this thought. The sides of a triangle or other polygon are mapped to the elements of another figure by parallel transfer, homothety, reflection from the axis, plane, rotation and other. Note that if such a mapping is reversible, mutually unambiguous, then a point remains a point, a segment remains a segment. Here dimensionality is preserved. The figure shows how two equivalent correct three-dimensional pyramids are mapped, say, while viewing a hologram. The principle of equivalence means that a small pyramid as a whole is mapped to a large 3D pyramid, an arbitrarily chosen face is mapped to a 2D face, a one-dimensional edge is mapped to a one-dimensional edge. Drawing and architecture are based on this principle, which has stood the test of time for at least 6 millennia. Why in this situation we cannot select hypermeridians on the sphere and expect that each of such elements will be mapped into the set of elements of the corresponding dimension? The dimension of the n-cube layer can be seen from the decomposition of Newton's binomial.
Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going, and you'll wind up with something.
Simplify its appearance to one layer. Use Pascal's triangle, where the binomial coefficient is written in rows. As a result, we will have the highest term in this polynomial disappear, and we will be left with the highest degree of only n-1. You can replace the sum sign with the union sign. Look at this corner, and this is a cascade of corner forming a cube together. The Cartesian product of a linear segment per square forms a cube. This indicates compliance with the principle of dimension. If we are working with a decorative material, such as siding for a house, it is common to measure it in square meters. Weathering products, such as lath or baseboard, are measured in meters. But in reality, all of the above materials have certain dimensions in length, height and width. However, minor dimensions are usually neglected. From the definition of topological space and Euclid's postulates, it follows that a unit cube or unit in degree n corresponds to a point in a space of dimension n. All the figures just listed are made of such unit cubes. They have the dimensions we are accustomed to by virtue of the axioms and the definition of topology. What is really an axiom in mathematics? It's the result of careful observation or a well-conducted experiment. Euclid's axioms are based on the principles of physics, which are homogeneity, isotropy, continuity of space. A point is equivalent to a point. In n-dimensional space, a point corresponds to a unit cube of degree n, not to some other cube. From this initial material, according to the rules of topology, it is possible to create figures of any natural dimensions from 1 to n.
A paradox arises. From the algebraic decomposition, it follows that figures in the form of a cube with a defect in the form of a missing point, corresponding to the expression I in degree n-1 or 2 in degree n-1, indifferent to elementary transformations, have dimensionality 1 unit less than the space in which these figures are created. Given the above, such expressions and figures correspond to a set of layers or a layer. But in the plane n equals 2, the figure corresponding to similar expressions remains two-dimensional. It is connected with the number of pairwise disjoint equivalence classes. On the plane, the simultaneous fulfillment of the conditions of symmetry preservation and equality of volumes inherent in Pythagoras' theorem is possible.
The most beautiful thing that can only strike us is the mystery. In our desire to unravel it lies the cradle of true art and true science. He who does not know this feeling has lost his curiosity and can no longer be surprised. He is like a dead man, like an extinguished candle. It is this feeling of mystery, though mixed with fear, that gave birth to religion. The realization that there is something we cannot understand, the deepest basis and root cause, the piercing beauty available to our minds only in the crudest forms. These are the knowledge and sensations that build true religiosity. In this sense, and in no one else, I am a deeply religious person. Albert Einstein, What Life Means to Einstein. The Sunday Evening Post, October 26, 1929.
Skepticism and objections. Some respected scientists object that piercing the n-dimensional cube with a two-dimensional plane is too simple and distorts the complex structure of this cube. This misunderstanding is caused by a poor representation of what the n-dimensional cube actually is. To illustrate the study, let us apply the method of setting up an experiment in virtual reality. Astronaut Fyodor went into multidimensional space to make a trip from the origin of coordinates and simultaneously the center of the 10-dimensional cube, whose faces are orthogonal to the coordinate axes, to an arbitrary vertex of the hypercube. The movements made by the astronaut imposed restrictions allowed movements only in the direction or against the direction of any of the n-coordinate axes. Fyodor made n jumps, the first one from the origin of coordinates to the center of the face of the highest dimensionality n-1, and all the rest, across the first jump. At each step or jump, Fyodor changed the direction of motion, turning at right angles.
Analysis of the experiment. Fyodor's report is as follows. Start from decaract. Moving to enact. Moving to octaract. Moving to heptaract. Moving to hexaract. Moving to pentaract. Moving to tesseract. Moving to cube. Moving to square. Moving to segment. Moving to vertex. Finish. In the last three steps we, as three-dimensional beings, could see the sudden appearance of Fyodor in the center of a three-dimensional cube from the invisible to us four-dimensional space, followed by a jump to the center of the wall, ceiling or floor, at the discretion of Fyodor, after which from a two-dimensional square, a jump to the center of the edge and finally, the last step, arrival at the vertex.
Analyzing the two-dimensional and three-dimensional cases and generalizing the result to the n-dimensional case, it is easy to calculate the length of the path of the root by Pythagoras' theorem or square root from scalar product vector on itself. The edge of an n-dimensional cube is located in the hyperplane perpendicular to the height just constructed and passing through the base of this height, the point of intersection of the straight line with this edge. Note that from Fyodor's point of view, all faces of the n-dimensional cube are perceived not as n-dimensional, but as flat figures. It is important to remember that Fyodor on his way observed multidimensional cubes with the effect of parallax. There are a number of examples from astronomy, everyday life, and works of visual art to explain this effect. Images of an n-dimensional cube are mesmerizing in their beauty. Let's imagine a projection of an n-dimensional cube onto a two-dimensional plane, for example, passing through the x, y axis, without the parallax effect. What figure will it be? The answer is a square. So, when we talked about piercing an n-dimensional cube with a probe, the Cartesian product of two probes perpendicular to different faces, we worked with induced topology. Without changing the generality, we can arrange the indexes of the coordinate axis in ascending, descending order and get the following result in the form of the ship log of cosmonaut Fyodor. At the end of the flight, we turn to the data of the auto-navigator, where Fedor's observations and directions of movement along each axis were recorded. From the basics of combinatorics, it is easy to see that the number of elements, the power of the set, consisting only of binary elements 0 and 1, is 2 to the power of n, exactly the same number of vertices in the n-dimensional cube. In this experiment, Fyodor started from the center of the 10-dimensional cube, moved only in the direction, denotes as 1, or against the direction, denoted as 0, successively explored all of its faces of dimension from 9 to 1. A perpendicular drawn from the center of a hypercube to any of its faces passes through its center. The length of the segment formed is half the length of its edge. This value is simultaneously the height of any of absolutely identical pyramids in the number of 2n pyramids, into which the n-cube is dissected. It is easy to see that the face of the n-dimensional cube is also a hypercube, but of dimension 1 less. In turn, this face includes its faces or edges of dimension n-2, n-3 and so on down to 1. Thus, the following concentric squares with sides, edges on the basis of a number of natural numbers as a result of piercing of an n-cube by a two-dimensional plane is a convenient tool for analyzing its topology. To physicists enough just one look at the cube to understand the proof of Fermat's last theorem. Let's transfer to the right side of the equation b in degree n with a minus sign and represent the construction in n-dimensional space corresponding to this expression. On the right you see a hypercube of dimension n, a symmetric figure. On the left you see a set of layers of dimension 1 less. This set will be asymmetric or will have an irrecoverable symmetry defect or violation of continuity of layers for dimension n/2. It is impossible to describe the same construction in such a contradictory way. There is a conflict in the properties of dimensionality, continuity, or symmetry. Hence, such a construction does not exist in nature. Interestingly, in the concentric sphere theories of the ancient Greeks Eudoxus, Callippus, and Aristotle, the Earth was at the center of the universe and surrounded by symmetrical spheres, all of which were considered perfectly symmetrical. But it turns out that even when we worked with our symmetrical spheres, we were convinced that this design did not correspond to any physical object in nature. Such a phenomenon was called in ancient Greece the aporia of logically consistent constructions that do not correspond to anything. It is surprising that we came to the same conclusion both for the case of working with n-cubes and balls. Absolutely symmetrical universe is impossible. For the origin of matter it is necessary to operate with the concept of volume, measure, and this is possible only in a slightly asymmetric, anisotropic space at n more than 2, but not in Euclidean space. The deep nature of this conflict stems from the fundamental physical properties of our universe. If it were perfectly symmetrical, like the studied construct of concentric spheres, then matter with its intrinsic properties of matter, measure conservation could not arise in it. This way, by investigating Fermat's last theorem, we have approached questions of physics and worldview without even applying higher mathematics, general relativity theory, and complex differential equations to illustrate the principles of the origin of our universe. The assumptions that were made within the framework of Euclidean geometry in relation to cosmic scales become inaccurate here. Non-Euclidean geometry is already at work. In anisotropic space, the conflict between the form and content of the structures we study is constructively resolved, but to do so, we must abandon Euclidean geometry. Here you are a portrait of the Russian scientist Nikolai Ivanovich Lobachevsky, the rector of Kazan University, a mathematician who carefully studied the fifth postulate of Euclid, whose axioms we have been considering, and formulated his own so-called imaginary geometry. This geometry was later called Lobachevsky's geometry. It turned out that Lobachevsky's geometry describes surprisingly well the concept of space-time interval, the Lorentz transformation.
And indeed, in 1983-84, the Russian relic experiment confirmed the anisotropy of relic radiation, the echo, of the Big Bang. The measurements were carried out with a radiometer developed at the Institute of Space Research of the USSR Academy of Sciences. In the group of Igor Arkadyevich Strukov, the general management of the program was carried out by academician Nikolai Semenovich Kardashev, on the launched satellite, Prognoz 9. In 2006, the discovery of Russian scientists was evaluated on merit by awarding the Nobel Prize in Physics to Americans George Smoot and John Mather for repeating the results of Russian physicists, but with greater precision. The names of Russian scientists remained in the shadows.
To complete our research, another quote: "Two things strike my imagination, starry sky and moral law within." Immanuel Kant.
As for me, I'd find it unacceptable to put artificial intelligence above the human mind in search for truth and verification of a mathematical proof. It goes against the principle of the cognizability of the world. Seek paradoxical and demonstrable proofs by relying on their own reason, observation, and experiment. The Fermat's last theorem plays a very interesting role in pedagogy. Nowadays, every student can make a discovery. I believe in future. I am an optimist. Thank you for your attention.